Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had one of those long, winding days where your mind hasn't quite stopped turning. Or perhaps you're the kind of person who likes to drift off to sleep while contemplating the quiet mysteries of the cosmos, rather than counting sheep or staring at the ceiling. Either way, you're exactly where you need to be. Tonight's journey is designed just for you. Before we begin our exploration, I want to mention that if these calm, curious wanderings through the universe help you unwind or give you a peaceful way to end your day, consider liking this video and subscribing to the channel. It helps other sleepy souls find their way here too, one restful night at a time. Now, settle in. Let your shoulders drop, your breathing slow, and your thoughts begin to float freely like particles drifting through the vastness of space. Tonight, we're going to talk about something you can't see, something so small that billions upon billions of these particles would fit on the head of a pin, yet something so profoundly important that without it, you wouldn't exist. We're going to explore space dust. Not the romantic stardust of poetry or songs, but the real, physical, scientific dust that fills the universe. The microscopic grains floating between stars, swirling in the spiral arms of galaxies, gathering in the cold, dark clouds where stars are born, and even drifting through our own solar system, some of it landing softly on Earth every single day. This dust is easy to overlook. For centuries, astronomers viewed it as nothing more than an annoying obstruction, something that got in the way of observing the stars and galaxies they really wanted to study. It blocked light, made observations difficult, and generally seemed like a cosmic nuisance. But then something changed. As our instruments improved and we learned to look at the universe in different wavelengths of light, particularly in infrared, we discovered that this dust isn't just debris cluttering up space. It's fundamental. It's the scaffolding upon which much of the universe is built. It plays a role in the birth of stars, the formation of planets, the chemistry that leads to life, and the very structure and appearance of galaxies. So tonight, as your eyes grow heavy and your mind begins to wander, let's drift together through the universe's hidden architecture. Let's discover the story of dust. What is space dust? The invisible architecture. When we talk about space dust, we're describing something almost impossibly small, yet unimaginably abundant. These are solid particles, tiny grains floating in the vast emptiness between stars, ranging in size from large molecules containing just a few dozen atoms, all the way up to particles about 1/10 of a millimeter across. That's smaller than the width of a human hair, smaller than grains of fine sand, almost at the very edge of what you could see if you had one of these particles sitting on your fingertip in bright light. But don't let their size fool you. Space dust makes up about 1% of the mass of our Milky Way galaxy. 1% might not sound like much until you remember that galaxies contain hundreds of billions of stars, vast clouds of gas, and enormous dark matter halos. That 1% of dust represents an almost incomprehensible amount of material spread throughout the galaxy, threading through every cubic light-year of space, hiding in plain sight. What exactly are these dust grains made of? The answer is beautifully complex. Most cosmic dust is composed of the same elements that were forged in the hearts of stars over billions of years. The primary ingredients are silicates, compounds of silicon and oxygen, often combined with magnesium, iron, and other metals. Think of them as microscopic pieces of something akin to sand or glass, though with a structure and composition often more irregular than anything you'd find on a beach. Some grains are crystalline, with atoms arranged in neat, orderly patterns. Others are amorphous, their atomic structure more chaotic and disordered, shaped by the violent conditions in which they formed. But silicates are only part of the story. A significant fraction of cosmic dust is carbonaceous, meaning it's made primarily of carbon. This carbon dust comes in several forms. Some of it is graphite, where carbon atoms bond together in flat hexagonal sheets. Some appears to be amorphous carbon, where the atomic arrangement is less structured. And, remarkably, scientists have found evidence of complex carbon molecules called polycyclic aromatic hydrocarbons, or PAHs. These are large organic molecules made of interconnected carbon rings with hydrogen atoms attached. They're the same sorts of molecules you'd find in the soot from a candle flame or the exhaust from a diesel engine. But these exist naturally in space, formed in the outflows of dying stars and drifting through the cosmos. In the coldest, densest regions of space, particularly in molecular clouds where new stars are being born, dust grains accumulate even more complexity. Ice mantles form on their surfaces, thin coatings of frozen water, carbon dioxide, methane, ammonia, and other volatile compounds. These icy layers can be tens of molecules thick, creating a kind of cosmic frost that clings to the grain cores. The presence of these ice mantles transforms the dust grains from simple refractory particles into complex, layered structures that serve as tiny chemical laboratories, places where molecules can meet, stick together, and react in ways that would be impossible in the tenuous gas of space. The dust grains themselves are not uniform or simple. They're irregular, often fluffy rather than compact, with shapes that defy easy description. Some are elongated, others more spherical. Many are aggregates, clumps of smaller grains that have stuck together over time, building up into larger, but still incredibly tiny composite structures. Their surfaces are rough and complex at the nanometer scale, full of nooks and crannies that provide shelter and reaction sites for atoms and molecules. Scientists have even been fortunate enough to examine actual interstellar dust grains, thanks to meteorites that fall to Earth. Embedded within some primitive meteorites are presolar grains, dust particles that formed around other stars before our solar system even existed, and somehow survived the violent processes of solar system formation. These ancient grains have been identified by their unusual isotopic compositions, atomic fingerprints that could only have been created in the nuclear furnaces of stars, very different from our Sun. They're time capsules, pieces of other stellar systems that have traveled across space and time to reach us, carrying within them the signatures of stellar processes billions of years old. These presolar grains include tiny diamonds, smaller than 1,000 nanometers across, their carbon atoms locked in that incredibly and crystalline structure. There are grains of silicon carbide, a tough compound that forms around carbon-rich stars. There are grains of graphite and various silicate minerals. Each type tells a story about the star where it formed, whether that was a red giant slowly puffing off its outer layers, or a supernova violently exploding and seeding space with freshly synthesized elements. The total picture that emerges is of a universe filled with countless trillions upon trillions of these microscopic grains, each one a complex object in its own right, together forming an invisible but absolutely crucial component of the cosmos. They float through space, sometimes isolated, sometimes gathered in clouds so dense they block out all visible light. They spiral through galaxies, drift through voids, rain down onto planets, and participate in an endless cycle of destruction and renewal that has been going on for most of cosmic history. The birth of dust. Stellar forges. Where does all this dust come from? The answer takes us to some of the most spectacular places in the universe. The dying breaths of stars. Stars are the universe's great alchemists. For most of their lives, they fuse lighter elements into heavier ones, building up the periodic table from hydrogen and helium into carbon, oxygen, nitrogen, silicon, iron, and all the other elements that make up the dust grains we've been discussing. But stars can't hold on to these elements forever. Eventually, they must return them to space, and it's often during this return journey, during the final stages of a star's life, that dust is born. Consider a star like our Sun, though perhaps a bit more massive. After billions of years of steadily converting hydrogen into helium in its core, it begins to run low on fuel. The core contracts and heats up, while the outer layers expand tremendously. The star swells into a red giant, its bloated atmosphere extending perhaps as far as Earth's orbit would be around our Sun. The outer layers of this giant star are cool by stellar standards, perhaps only a few thousand degrees, and relatively dense. In these cool, dense regions, conditions become right for dust to condense. Atoms of silicon, oxygen, carbon, and metals begin to stick together in the gentle outflow from the star's surface. Temperature and pressure conditions allow chemical bonds to form, and tiny solid particles begin to grow. If the star is oxygen-rich, having more oxygen than carbon in its atmosphere, silicate dust forms. Grains of olivine, pyroxene, and other silicon-oxygen compounds nucleate and grow, particle by particle. If the star is carbon-rich, having undergone changes in its nuclear burning that brought more carbon to the surface, then carbon dust forms instead. Graphite, amorphous carbon, and even silicon carbide grains. These dust grains form right in the stellar outflow, bathed in the star's intense light. As they grow, radiation pressure from the starlight pushes on them, accelerating them outward. This is how stars lose mass in their old age, puffing off layers of gas and dust that drift into space at speeds of perhaps 10 or 20 kilometers per second. Over thousands of years, the star might lose a significant fraction of its mass this way, ejecting material that will become part of the interstellar medium, mixing with gas and dust from other stars, enriching space with the products of stellar nucleosynthesis. The most visually spectacular dust-producing events are planetary nebulae, though despite the name, they have nothing to do with planets. A planetary nebula forms when a red giant star finally exhausts all its nuclear fuel and ejects its outer layers in a series of gentle exhalations. What remains is the hot, dense core of the star, now a white dwarf, which illuminates the expanding shells of gas and dust with intense ultraviolet light. The result is one of nature's most beautiful displays. Glowing, sculpted clouds of gas in vivid colors, embedded with microscopic dust grains that were forged in the star's final days. But red giants and planetary nebulae aren't the only stellar dust factories. Some of the most productive sources are stars on the asymptotic giant branch, or AGB stars for short. These are evolved stars in a brief but prolific phase of life where they pulsate, expanding and contracting periodically. With each pulsation, material is lifted from the surface into cooler regions where dust can form. These stars are proteus dust producers. Observations have shown that Mira variables, a type of AGB star, and other long-period variables can inject enormous quantities of dust into the galaxy. In fact, by some estimates, AGB stars may contribute about 30% or more of all new dust to the interstellar medium. Then there are the violent dust makers, supernovae. When a massive star reaches the end of its life, its core collapses catastrophically, and the star explodes with unimaginable force, briefly outshining an entire galaxy. In the aftermath of this explosion, the expanding debris cloud contains freshly synthesized heavy elements, and as this material cools over months and years, dust begins to condense. Supernova dust is particularly interesting because it can contain unusual compositions, including large amounts of radioactive isotopes that have since decayed, but left their mark in the isotopic ratios of presolar grains found in meteorites. For a long time, astronomers debated how much dust could really form in supernovae. Early theories suggested these explosions should be major dust sources, but observations seem to show only modest amounts of dust forming in supernova remnants. This created what's called the dust budget problem, a mismatch between how much dust we observe in distant young galaxies and how much we think should be produced by known sources. More recent observations, particularly with infrared space telescopes that can peer through gas to see cool dust, have suggested that supernovae might produce more dust than previously thought, though the debate continues. Wolf-Rayet stars, massive stars in a brief, intense phase of evolution, also contribute dust. These stars have lost their outer hydrogen layers through powerful stellar winds and now burn with exposed helium and carbon layers. Some Wolf-Rayet stars, particularly those rich in carbon, can produce copious amounts of carbon dust that streams away in their winds. And so, across the galaxy, in the final breaths of stars of all types, dust is continually being born. It starts as simple molecules coming together in hot stellar winds, or cooling supernova ejecta. It grows grain by grain, accreting more material, until microscopic particles drift away from their stellar birthplaces and enter the great ocean of the interstellar medium. This is how the universe recycles itself, how stars take the primordial hydrogen and helium from the Big Bang, forge them into heavier elements, and then return those elements to space in the form of gas and dust that will one day become the raw material for new stars, new planets, and perhaps even new life. Interstellar dust, the galaxy's hidden fabric. Once dust grains leave their stellar birthplaces, they enter a very different environment. The interstellar medium, the vast expanse of space between the stars. Here, dust grains begin a long journey that might last millions or even billions of years, during which they will be battered, modified, destroyed, and potentially incorporated into new structures. The interstellar medium is far from empty, though it's certainly sparse by earthly standards. It's a thin soup of gas, primarily hydrogen and helium, with a dash of heavier elements and about 1% by mass of solid dust grains. The density varies enormously from place to place. In the diffuse interstellar medium, the spaces between the denser clouds, you might find only 1 atom per cubic centimeter. That's a better vacuum than anything we can create in laboratories on Earth. Yet, even in this incredibly tenuous environment, dust grains drift, tumble, and occasionally collide with gas atoms or other grains. The dust in this diffuse medium has a major impact on how we see the universe. Dust grains are very effective at blocking light, particularly at shorter wavelengths. When starlight passes through a dust cloud, the blue and ultraviolet light gets scattered and absorbed much more efficiently than red light. This causes 2 effects that astronomers have known about for over a century. First, stars appear dimmer than they actually are, an effect called interstellar extinction. Second, stars appear redder, an effect called interstellar reddening. It's similar to how Earth's atmosphere makes the sun appear red at sunset, when sunlight has to pass through more air and the blue light gets scattered away, except in space it's dust doing the scattering instead of air molecules. This extinction and reddening complicates astronomy. If you want to know how bright a star really is, you need to account for how much light has been absorbed or scattered by intervening dust. If you want to measure a star's true color and use that to determine its temperature, you need to correct for the reddening caused by dust. For decades, astronomers worked to map out the extinction properties of interstellar dust, measuring how much extinction occurs at different wavelengths to better understand both the dust itself and the stars they were trying to study. But dust doesn't just block light passively. In regions where a bright star illuminates nearby dust, we can see reflection nebulae, beautiful glowing clouds of gas and dust lit up by starlight. The dust scatters the star's light, making the nebula shine with a ghostly blue glow. The Pleiades star cluster, visible to the naked eye as a small dipper-shaped group of stars, is surrounded by wispy blue reflection nebulae created by dust grains scattering the light of these young, hot stars. In denser regions of the interstellar medium, dust accumulates into molecular clouds, vast structures spanning tens or even hundreds of light years. These clouds are cold, typically only 10 or 20 degrees above absolute zero, and dense enough by astronomical standards that molecules can form and survive. Here, dust grains acquire their ice mantles. Water molecules from the gas phase stick to grain surfaces and freeze. So do carbon monoxide, carbon dioxide, methane, ammonia, and various organic molecules. Over time, layers of ice build up, creating complex, stratified grain mantles that can be several tens of molecules thick. These icy grains play a crucial role in the thermal physics of molecular clouds. The dust absorbs any ultraviolet and visible light that manages to penetrate into the cloud, converting that radiation into heat. But then the dust radiates that heat away in the form of infrared light, which can then escape from the cloud more easily. This cooling mechanism helps keep molecular clouds cold, which is essential for allowing them to collapse under their own gravity to form new stars. Without dust, molecular clouds would be much warmer and more difficult to collapse. The dust also provides the only significant source of opacity in molecular clouds. When we look at regions like the Horsehead Nebula or the Pillars of the Eagle Nebula, those dark, silhouetted structures are molecular clouds where dust is so abundant that it blocks all visible light from stars behind them. These aren't voids or empty regions. They're among the densest places in the galaxy, regions so packed with gas and dust that light cannot pass through. Infrared telescopes, which can penetrate the dust, reveal these dark regions to be teeming with activity, with young stars forming, protoplanetary disks swirling, and complex chemistry unfolding on the surfaces of dust grains. Across our Milky Way galaxy, dust creates the striking dark lanes we see bisecting the bright band of the galaxy across the night sky. The galactic plane, where most of the galaxy's stars reside, also contains most of its dust, and that dust blocks our view of the stars on the far side of the galaxy. We cannot see the galactic center in visible light, not because there aren't stars there, quite the opposite, but because thousands of light years of intervening dust blocks our view. Only in infrared, radio, and X-ray wavelengths can we peer through or around the dust to see the crowded stellar metropolis and the supermassive black hole at the galaxy's heart. The dust lane in a spiral galaxy seen edge-on is a defining feature. Look at images of galaxies like the Sombrero Galaxy, and you'll see a thick, dark stripe cutting across the galactic disk. That's dust. Countless billions of dust grains, making their presence known by the light they block rather than by any light they emit. From our vantage point within the Milky Way, we're looking through our own dust lane, which is why we see the galaxy as a luminous band rather than a face-on spiral. The grains themselves, floating in the interstellar medium, don't remain unchanged. Ultraviolet light from hot stars can break chemical bonds, sputtering atoms off grain surfaces and slowly eroding them. Cosmic rays, high-energy particles streaming through the galaxy, strike grains and cause radiation damage. When fast-moving supernova shock waves slam into clouds, they can shatter grains or vaporize them entirely. Yet new grains continue to form, both from stellar sources and potentially through chemistry in the interstellar medium itself, where atoms and molecules might stick together on existing grain surfaces, slowly building up new material. This is the dynamic, ever-changing realm of interstellar dust. It shapes the appearance of galaxies, influences the behavior of light, helps regulate the temperature of space, and sets the stage for the most important role dust plays in the universe, enabling the birth of stars and planets. Cosmic chemistry. Dust as a laboratory. Dust grains, despite their tiny size, are profoundly important to the chemistry of the universe. In the cold, tenuous environment of space, gas phase chemical reactions are difficult. Atoms and molecules are spread so far apart that they rarely encounter each other. Even when they do meet, many reactions require three bodies to be present simultaneously: two reactants and a third particle to carry away excess energy, so the reaction products remain stable. In the sparse interstellar gas, three-body encounters are vanishingly rare. But dust grains change everything. A dust grain surface provides a meeting place, a two-dimensional stage where atoms and molecules can stick, accumulate, encounter each other, and react. Even better, the grain itself can act as that third body, absorbing or releasing energy to facilitate reactions. This surface chemistry on dust grains is essential to the formation of molecules in space, particularly hydrogen molecules, the most abundant molecule in the universe. Hydrogen molecules don't form efficiently in the gas phase. Two hydrogen atoms meeting in empty space will briefly touch, but without a way to shed their excess binding energy, they'll just bounce apart again. But on a dust grain surface, the process works beautifully. A hydrogen atom wanders through space and strikes a grain. If the grain is cold enough and the surface has the right properties, the hydrogen atom sticks. It might be bound weakly by van der Waals forces, or it might actually form a chemical bond with atoms on the grain surface. Either way, it's now held in place, waiting. Eventually, a second hydrogen atom strikes the grain near where the first one is stuck. Now, instead of passing each other in the emptiness of space, they're close neighbors on the grain surface. They can migrate slightly, hopping from binding site to binding site until they meet. When they do, they react, forming a hydrogen molecule. The excess energy from this reaction flows into the grain, warming it very slightly, while the newly formed molecule, having received a small kick from the reaction energy, might break free from the surface and float away into space. Over and over, across countless dust grains throughout the galaxy, this process repeats, building up the vast reservoirs of molecular hydrogen we observe in molecular clouds. But the chemistry doesn't stop with hydrogen. The ice mantles on grains in cold, dense clouds become sites of complex chemical processing. Ultraviolet light from distant stars, though weak, still penetrates into clouds enough to drive photochemistry. When a UV photon strikes an icy grain mantle, it can break chemical bonds, creating reactive fragments called radicals. These fragments are trapped in the ice, unable to escape, but able to migrate slowly through the ice matrix. When they encounter other radicals or molecules, they can react, forming new and more complex compounds. Through this process, simple ices transform into complex mixtures. Water, carbon monoxide, methanol, ammonia, and formaldehyde all appear in ice mantles. So do more complex molecules, ethanol, glycolaldehyde, and various organic acids. Even more remarkably, laboratory experiments simulating interstellar ice chemistry have produced amino acids, the building blocks of proteins, and other prebiotic molecules. The implication is stunning. The cold surfaces of microscopic dust grains, bathed in starlight in the depths of molecular clouds, are creating the chemical precursors to life. Polycyclic aromatic hydrocarbons, those complex carbon molecules mentioned earlier, also play a chemical role. They're abundant in space and remarkably stable. They absorb ultraviolet light very efficiently and then re-emit the energy in the infrared. In the process, they help heat the gas in regions like the surfaces of molecular clouds or the edges of regions where massive stars have formed. PAHs might also catalyze certain reactions or provide surfaces for molecule formation, though their exact role is still being researched. The discovery of presolar grains in meteorites has given scientists an unprecedented window into stellar chemistry. By examining individual grains under electron microscopes and using mass spectrometry to measure their isotopic compositions with incredible precision, researchers can determine exactly where and when these grains formed. The isotopic fingerprints are distinctive. A grain that formed around a red giant star will have different ratios of carbon, nitrogen, and oxygen isotopes than a grain from a supernova. Some grains even contain now extinct radioactive isotopes, elements that were alive when the grain formed but have since decayed. The presence of titanium-44, with a half-life of only 59 years in some silicon carbide grains, is considered evidence that those grains formed in a supernova explosion and were ejected into space before the titanium had time to decay. These presolar grains also contain complex organic matter. Some carbonaceous grains found in meteorites are rich in aromatic structures and contain evidence of organic compounds more complex than anything we might have expected to form in space. It appears that the chemistry occurring in stellar outflows and in the interstellar medium is remarkably sophisticated, capable of building molecular architectures that approach the complexity needed for biochemistry. Water itself, that most essential molecule for life as we know it, forms primarily on dust-grain surfaces in space. In the densest parts of molecular clouds, nearly all the oxygen not locked into carbon monoxide ends up as water ice on grain surfaces. When these clouds eventually collapse to form stars and planetary systems, that water comes along, potentially delivering oceans worth of water to forming planets and moons. Earth's water might have come, at least in part, from icy dust grains and the comets and asteroids that incorporated that primordial ice. The picture that emerges is of dust grains as tiny chemical factories scattered throughout space, each one facilitating reactions that would be impossible or extremely slow in the gas phase alone. The surfaces of these grains are where the universe builds complexity, where simple atoms combine into molecules, where molecules combine into more complex structures, where the raw materials for life are assembled in the cold dark between the stars. Star formation, dust as architect. All the chemistry and complexity that dust enables would be interesting on its own, but dust's most important role in the universe is architectural. It helps build stars and planetary systems. Star formation begins in molecular clouds, those cold, dark regions where gas and dust have accumulated to high densities. For a molecular cloud to collapse and form stars, it needs to overcome several obstacles. It has internal pressure from the random motions of gas molecules that pushes outward trying to disperse the cloud. It has magnetic fields threading through it that provide additional support. And it has turbulence, chaotic swirling motions that can fragment the cloud but also provide support against collapse. Gravity, of course, wants to pull the cloud together. Whether gravity wins depends on the balance between gravitational energy pulling inward and all the forces pushing outward. This is where dust becomes crucial. By helping to cool the gas, dust tips the balance in gravity's favor. Here's how it works. As a region within a molecular cloud begins to contract under its own gravity, the gas heats up slightly. If that heat couldn't escape, the rising pressure would halt the collapse. But dust grains, being solid particles, are much better at radiating heat than gas molecules are. They absorb the thermal energy from gas collisions, warm up very slightly, and then radiate that heat away as infrared light. This infrared radiation can escape from the cloud fairly easily, carrying energy away. The result is that the cloud stays cool even as it contracts, allowing gravity to continue pulling the material together. Without dust, star formation would be much less efficient, possibly so inefficient that galaxies would look entirely different. The universe might have far fewer stars, or star formation might proceed by a completely different mechanism. Dust, that seemingly trivial 1% of cosmic matter, is essential to populating the universe with stars. As a region of a molecular cloud collapses, it fragments into smaller pieces, each of which might form a star. The center of each collapsing fragment becomes denser and hotter, forming a protostar, a baby star not yet hot enough in its core to begin nuclear fusion. Around this protostar, material that didn't fall directly inward settles into a rotating disk, a protoplanetary disk composed of gas and dust inherited from the parent molecular cloud. These protoplanetary disks are where planets form, and dust plays the starring role. Initially, the dust grains are still microscopic, the same sizes they were in the interstellar medium. But now they're in a much denser environment, orbiting around a forming star, and they begin to stick together when they collide. The process starts gently. Two dust grains touch, and weak forces, van der Waals forces and static electricity, hold them together. The grains don't bounce apart. Instead, they form a slightly larger particle. This process continues. Small aggregates stick together to form larger ones. Over time, perhaps a few thousand years, the dust has grown from microscopic grains to pebbles a centimeter or more across. This stage, from dust to pebbles, is relatively well understood. The tricky part comes next, growing from pebbles to planetesimals, objects kilometers in size. This is called the meter-size barrier because theoretical models suggest that meter-sized objects in a protoplanetary disk should spiral into the star very rapidly due to gas drag, faster than they can grow to larger sizes. The solution to this problem is still debated, but several mechanisms have been proposed. One involves the concentration of pebbles in certain locations in the disk, perhaps in vortices or at pressure maxima, where they become dense enough to collapse gravitationally into larger bodies all at once. Another involves the direct growth through continued sticky collisions. perhaps aided by ice or organic compounds that make particles more adhesive. Whatever the mechanism, it works. We see the evidence all around us. Planets, moons, asteroids, and comets, all built ultimately from dust. In the outer parts of protoplanetary disks, beyond what's called the snow line where water can freeze, ice-coated dust grains are particularly sticky and grow more easily. This is thought to be why the giant planets in our solar system formed in the outer regions. They grew large, solid cores quickly from ice-coated dust, and those cores became massive enough to gravitationally capture enormous atmospheres of hydrogen and helium. The inner planets, forming inside the snow line where ice couldn't exist, had a harder time growing large and ended up as smaller, rocky worlds. The dust in protoplanetary disks doesn't just build planets, it also influences the structure of the disk itself. As dust settles toward the midplane of the disk, it creates a thin, dense layer where most of the solid material resides. This layer is where planet formation is most efficient. The dust also helps transport angular momentum in the disk through various complex interactions with the gas, influencing how material flows and how the disk evolves over time. Observations of protoplanetary disks around young stars have revolutionized our understanding of planet formation. Using powerful telescopes like the Atacama Large Millimeter Array, ALMA, astronomers can now image these disks in exquisite detail. They see gaps and rings in the dust distribution, features likely carved by forming planets. They see spiral structures, asymmetries, and other patterns that reveal the dynamic processes at work. These observations confirm that planet formation is happening right now, in real time, in disks around stars throughout our galaxy and beyond. From a half-light, year-wide molecular cloud to a star surrounded by planets, dust is present at every stage, playing critical roles. It helps the cloud cool and collapse. It forms the solid cores of planets. It delivers water and organic compounds to those planets. Every solid object in the solar system, from the smallest grain of asteroid dust to the rocky cores of the giant planets to the ground beneath our feet, is made from dust that formed billions of years ago in the winds of dying stars, drifted through the interstellar medium, gathered into a molecular cloud, and eventually came together to build a new solar system. We are, quite literally, made of stardust. Our solar system's dust. Dust didn't disappear from our solar system once the planets finished forming. It remains abundant, creating phenomena that humans have observed for thousands of years without understanding what they were seeing. If you find yourself far from city lights, in a desert or on a remote mountaintop, and look at the sky just after sunset or just before sunrise, you might see something strange. A faint, ghostly pyramid of light extends upward from the horizon. Tilted along the path of the sun and the planets follow across the sky. The ancient Greeks saw this glow and called it zodiacal light, because it appears in the band of constellations we call the zodiac. For a long time, people wondered what it was. Some thought it was sunlight reflecting off Earth's upper atmosphere. Others speculated it might be a part of the sun's outer atmosphere extending into space. The truth, we now know, is dust. The zodiacal light is sunlight scattered by countless millions of dust particles spread throughout the inner solar system. These particles form a thick, pancake-shaped cloud called the zodiacal cloud, concentrating near the ecliptic plane where the planets orbit. The dust grains themselves are tiny, typically tens to hundreds of micrometers across, sizes comparable to particles in cigarette smoke or fine flour. For decades, astronomers debated the source of this dust. Comets seemed like likely culprits. As comets approach the sun, solar heat vaporizes their ice, and jets of gas carry dust particles off the comet's surface into space. Some of this dust remains in orbit around the sun, gradually spreading out along the comet's path. Asteroids also contribute. When asteroids collide in the main asteroid belt, they shatter, creating fragments and dust that slowly spirals inward toward the sun or outward away from it. But recent discoveries have added a surprising twist to this story. Data from NASA's Juno spacecraft, which was designed to study Jupiter, but also carried instruments that detected dust impacts, has provided strong evidence that Mars might be a major source of zodiacal dust. Mars is the dustiest planet in the solar system, with planet-wide dust storms that loft fine particles high into its thin atmosphere. Some of this dust might escape Mars's weak gravity entirely and enter orbit around the Sun. The Juno data showed that the density of dust particles peaked near Mars' orbit and dropped off in ways consistent with Mars being a primary source. This was surprising because no one had seriously considered Mars as a significant dust producer for the zodiacal cloud. The mechanism by which dust escapes from Mars is still not fully understood, but the observational evidence is compelling. It's a reminder that even in our own solar system, studied intensely for centuries, surprises still await. The zodiacal dust doesn't last forever. Several processes remove it from the solar system on timescales much shorter than the solar system's age. Radiation pressure from sunlight pushes on the small grains, and the smallest ones are actually expelled from the solar system entirely. Larger grains feel a more subtle effect called Poynting-Robertson drag. As a dust grain orbits the sun, it absorbs sunlight on its leading face and re-radiates that energy as heat in all directions. This creates a tiny but persistent drag force that causes the grain's orbit to slowly spiral inward toward the sun. Over thousands to millions of years, depending on the grain's size, it will eventually spiral all the way into the sun and be vaporized. Collisions between dust grains also break them into smaller fragments, which are then more easily removed by radiation pressure or drag. Given these removal mechanisms, the zodiacal cloud must be continuously replenished. The dust we see today isn't primordial material left over from the solar system's formation. It's almost entirely later generation dust, material released in the last few million years from comets, asteroids, Mars, and possibly other sources. The primordial dust has long since been swept away. Beyond the zodiacal cloud, dust exists elsewhere in the solar system. Planetary rings are made largely of dust and ice particles. Saturn's magnificent ring system, visible even in a small telescope, is composed of countless particles ranging from micrometers to meters in size, all orbiting the planet in a paper-thin disk. Jupiter, Uranus, and Neptune also have ring systems, though much fainter than Saturn's, made primarily of fine dust. Dust also surrounds some moons. Jupiter's moon Io, the most volcanically active body in the solar system, constantly spews dust into space from its eruptions. This dust spreads out along Io's orbit, forming a tenuous ring around Jupiter. Other moons, particularly those with geysers like Saturn's Enceladus, also contribute dust to their local environments. And dust is falling on Earth constantly. Every day, our planet sweeps up tons of cosmic dust as it orbits the Sun. Estimates vary, but a commonly cited figure is around 40 tons per day, or roughly 15,000 tons per year. Most of these particles are so small that they drift gently down through the atmosphere without burning up. They settle onto the ground, onto rooftops, into the oceans. You're breathing them right now, though they're so dilute and small that you'd never notice. Some of this dust can be collected and studied. Scientists have used aircraft flying at high altitudes to collect interplanetary dust particles directly from the stratosphere, before they've had a chance to be contaminated by terrestrial material. These particles are analyzed in clean rooms using electron microscopes and other sensitive instruments. They've revealed a fascinating variety of structures and compositions, providing ground truth for our understanding of cosmic dust that we otherwise only observe from great distances. The Stardust mission, launched by NASA in 1999, was designed specifically to collect dust-Oreos particles from a comet and return them to Earth. The spacecraft flew through the coma of Comet Wild 2 in 2004, capturing dust particles in a special aerogel collector. The sample return capsule parachuted back to Earth in 2006, and scientists have been studying the captured particles ever since. These comet dust grains are among the most primitive material in the solar system, largely unchanged since the comet formed over 4 billion years ago. They contain presolar grains, organic compounds, and minerals that recorded conditions in the early solar system. Remarkably, the mission also captured a few particles of interstellar dust that happened to be passing through the solar system, making them the first confirmed interstellar dust particles ever returned to Earth for laboratory study. Our solar system's dust, then, is a mixture of old and new, local and foreign. It includes particles eroded from asteroids and Mars, fragments blasted off comets, grains ejected from Jupiter's moons, and the occasional visitor from interstellar space. It creates visible phenomena like zodiacal light, contributes to meteors and fireballs as larger particles burn up in Earth's atmosphere, and constantly, invisibly rains down on our planet, adding a tiny but continuous influx of extraterrestrial material to Earth's surface. In a very real sense, cosmic dust is always around us, above us, and on us, connecting us physically to the larger universe. Observing dust, light and shadow. For astronomers, dust has always been a double-edged sword. It obscures things we want to see, making observations more difficult. But it also reveals information about the universe that we couldn't learn any other way. The obscuration problem was recognized as far back as the 18th century. Astronomer William Herschel noticed that some regions of the Milky Way appeared to have very few stars, as if there were holes or tunnels through the galaxy. He called these dark regions holes in the heavens. We now know these aren't empty voids, but rather dense dust clouds blocking the light from stars behind them. The dust isn't emitting any visible light itself, and it's absorbing and scattering light from background stars, creating what looks like a dark patch against the bright backdrop of the Milky Way. This effect frustrated astronomers for a long time. When they tried to map the distribution of stars in the galaxy, the dust made it look like there were fewer stars in certain directions, distorting their maps. When they tried to measure how far away stars were by how bright they appeared, dust made distant stars look dimmer and therefore seem farther than they really were. When they tried to determine a star's temperature from its color, dust made stars appear redder and thus cooler than they actually were. Gradually, astronomers learned to account for dust. By measuring how much a star's color had been reddened, they could estimate how much extinction had occurred and correct the star's observed brightness. By studying the wavelength dependence of extinction, they learned about the sizes and properties of dust grains. The famous 2175 angstrom bump, a feature in the extinction curve where dust absorbs particularly strongly in the ultraviolet, has been attributed to graphite grains or perhaps PAHs, though the exact cause is still debated. The real revolution in studying dust came with infrared astronomy. Dust grains, especially those heated by starlight, glow in the infrared. By observing the universe in infrared wavelengths, astronomers could see the dust itself emitting light, rather than just blocking it. This opened up entirely new vistas. In the 1960s and 70s, pioneers of infrared astronomy began flying detectors on balloons, rockets, and eventually satellites to get above Earth's atmosphere, which absorbs most infrared light. They discovered that many celestial objects glow brightly in the infrared due to dust. Galaxies that appeared modest in visible light blazed brilliantly in the infrared. Entire regions of the Milky Way, dark, invisible images, lit up with infrared emission from warm dust. NASA's Infrared Astronomical Satellite, IRS, launched in 1983, was a landmark mission. It surveyed the entire sky in infrared wavelengths and discovered hundreds of thousands of infrared sources, many of them dusty regions of star formation, dust-enshrouded galaxies, and even dust around nearby stars that might indicate the presence of planetary systems. IRAS showed that the universe is full of dust, and that much of the universe's light, emitted by stars, is absorbed by dust and re-radiated in the infrared. Later missions built on IRAS's legacy. The Spitzer Space Telescope, launched in 2003, provided far more sensitive infrared observations. Spitzer could peer into molecular clouds and see dust structures and forming stars hidden from visible light telescopes. It mapped the distribution of PAHs across galaxies. It studied proto-planetary disk-round young stars, revealing gaps and structures that indicated planet formation in progress. Spitzer observations showed it that dust is an active participant in galactic evolution, not just a passive tracer. The Herschel Space Observatory, launched in 2009, observed at far infrared and submillimeter wavelengths where the coldest dust glows. Herschel mapped cold dust in molecular clouds, traced the early stages of star formation and studied dust in distant galaxies. It revealed that much of the universe's star formation happens hidden behind veils of dust, detectable only in the infrared. Now, the James Webb Space Telescope, launched in 2021, is pushing infrared astronomy to new extremes. JWST's unprecedented sensitivity and resolution allow it to image dusty regions with extraordinary clarity. It can see through the dust lanes in galaxies, revealing stellar populations previously hidden. It can study the atmospheres of exoplanets by watching starlight filter through dusty disks. It can observe the most distant, dusty galaxies in the early universe, helping us understand how galaxies and the dust evolved together over cosmic time. But infrared observations alone don't tell the whole story. Astronomers also use polarimetry, measuring the polarization of starlight that has passed through or been scattered by dust. Dust grains are typically not spherical, and they tend to align with magnetic fields in the interstellar medium. This alignment causes them to polarize starlight preferentially in certain directions. By measuring this polarization, astronomers can map the structure and orientation of magnetic fields in clouds and galaxies, information that would be nearly impossible to obtain any other way. Radio astronomy also contributes to dust studies. While dust itself doesn't emit strongly at radio wavelengths, radio telescopes can observe the gas associated with dust, particularly the radio emission from cold hydrogen molecules and from other molecules that form on dust grains. This allows astronomers to map the distribution of molecular clouds and correlate it with dust observations. Laboratory work complements astronomical observations. Scientists recreate interstellar conditions in vacuum chambers, forming dust analog particles and subjecting them to ultraviolet light, cosmic ray impacts, and temperature cycling to see how they change. These experiments help interpret observations and test theories about dust evolution. Meteorite studies provide actual samples of dust to analyze, offering ground truth that can't be obtained any other way. Dust detection has even gone interplanetary. Spacecraft like Ulysses, Galileo, and Cassini carried instruments to detect dust impacts in space. These instruments can't capture intact dust grains at the high relative velocities involved, but they can measure the size, speed, and to some extent the composition of dust particles by analyzing the impact debris. This has allowed scientists to study interplanetary dust, dust around planets and moons, and even interstellar dust passing through the solar system. Through all these methods, observations, missions, and experiments, our understanding of cosmic dust has grown from an annoyance to be corrected for to a fascinating and essential component of the universe worthy of study in its own right. We now recognize dust as a tracer of astrophysical processes, a participant in chemistry and star formation, and a carrier of information about conditions in the cosmos, both near and far. Dust through time, the recycling universe. Dust is not immortal. Individual dust grains come and go, created and destroyed in an endless cycle that has been operating for most of the universe's history. Understanding this cycle is crucial to understanding how galaxies and stars evolve over cosmic time. We've already discussed how dust forms primarily in the winds and ejecta of dying stars. But dust is also destroyed, and the destruction mechanisms are powerful. Supernova shock waves are particularly efficient at obliterating dust. When a supernova explodes, it sends a blast wave expanding outward at speeds of thousands of kilometers per second. When this shock wave slams into the surrounding interstellar medium, it creates extremely harsh conditions. The sudden compression heats the gas to millions of degrees. The shock can shatter dust grains, breaking them into smaller fragments. It can vaporize them entirely, returning their atoms to the gas phase. In the most intense shocks, dust can be completely destroyed in a matter of decades or centuries, undoing millions of years of gradual grain growth in an instant. This creates what's called the dust budget problem. When astronomers calculate how much dust should be destroyed by supernova shocks versus how much should be produced by stellar sources, the destruction seems to far outpace the production. By some estimates, the average lifetime of a dust grain in the interstellar medium should be only a few 100 million years before it's destroyed by a shock. But stars take billions of years to evolve and eject dust. The math doesn't add up. There should be far less dust in the galaxy than we actually observe. Several solutions to this problem have been proposed. One possibility is that dust can reform quickly in the interstellar medium. Perhaps atoms and molecules can stick together on existing grain surfaces, gradually rebuilding grains after they've been eroded or partially destroyed. This process, called grain growth by accretion in the ISM, could help replenish the dust population between episodes of creation in stars and destruction in shocks. Another possibility is that we've underestimated how much dust is produced in supernova. Early observations of young supernova remnants showed only small amounts of dust. But more recent observations with sensitive infrared telescopes have found much more dust than expected, hidden in cool regions that don't emit visible light. If supernovae produce more dust than we thought, that could help balance the budget. Yet another factor is that not all dust in the path of a supernova shock is necessarily destroyed. Some grains might survive in denser clumps that the shock hasn't fully penetrated yet. Others might be processed rather than destroyed, sputtered down to smaller sizes but not completely vaporized. The survival rate of dust in shocks is still uncertain and depends on many factors, including the shock speed, density, and the composition and size of the grains. Whatever the exact balance, it's clear that dust undergoes continuous cycling. A grain might form in the wind of a red giant star and drift into the interstellar medium. It might accrete an ice mantle in a molecular cloud. It could be partially eroded by a passing shock wave. The remaining core might accrete more material over time, growing again. Eventually, it might be incorporated into a new molecular cloud that collapses to form stars. If it ends up in a protoplanetary disk, it might stick to other grains and eventually become part of a planet or asteroid. Or it might be vaporized when it drifts too close to the forming star, its atoms returning to the gas phase to potentially form new dust grains someday. This cycle has been operating throughout the history of the universe. In the very early universe, shortly after the Big Bang, there was no dust. The first stars, formed from primordial hydrogen and helium, contained no heavy elements at all. But when these first stars died, they created the first dust, grains made from the carbon, oxygen, and silicon forged in their cores. This first generation of dust enriched the interstellar medium, mixing with gas to form the next generation of stars, which were already slightly richer in heavy elements. Over billions of years, repeated cycles of star formation, stellar evolution, dust creation, dust destruction, and renewed star formation gradually enriched the universe. Each generation of stars contained more heavy elements than the last. More dust formed. Galaxies grew dustier over time. The dust itself evolved in composition, as different types of stars contributed different elements. When we observe very distant galaxies, we're seeing them as they were billions of years ago due to the finite speed of light. Remarkably, even galaxies in the very young universe, less than a billion years after the Big Bang, contain substantial amounts of dust. This was surprising because there should have been less time for stars to form, evolve, and produce dust. The presence of large amounts of dust in these early galaxies suggests that dust formation must have been very efficient in the early universe, possibly because the first generations of massive stars evolved quickly and supernovae were very dusty. Dust observations of distant galaxies also reveal that much of the star formation in the universe's history has been obscured by dust. In visible light, we see some galaxies forming stars at certain rates. But when we add infrared observations that can see through the dust, we discover that the actual star formation rates are often much higher. Some galaxies are ultra-luminous in the infrared, powered by enormous bursts of star formation hidden behind thick dust clouds. These dusty starbursts are thought to occur when galaxies collide and merge, triggering intense waves of star formation. The story of cosmic dust is thus intimately tied to the story of cosmic evolution. Dust traces the chemical enrichment of the universe. It shapes how galaxies look and how they form stars. It carries the heavy elements made in stars back into space to build new stars and planets. Every atom in your body has likely been through this cycle multiple times, forged in a star, ejected into space, incorporated into dust, perhaps destroyed and reformed, eventually gathered into our solar system, and finally assembled into a living organism on Earth. As you lie here, perhaps on the edge of sleep, consider that the atoms in your hand were once scattered as individual dust grains drifting through the galaxy. The iron in your blood was formed in a supernova explosion and condensed into dust grains that survived for millions or billions of years before finding their way here. You are made of recycled stardust, and when you die and decay, those atoms will return to the environment. Long after humans are gone, perhaps those atoms will one day be ejected from Earth by a collision or blown off by solar wind, drifting once again through space as dust, to someday perhaps be incorporated into a new world around a distant star. The universe recycles everything, and dust is the currency of that recycling. Closing reflections and call to action. And so we've drifted through the hidden universe of dust. From the microscopic grains drifting in interstellar space to the glowing zodiacal light in our own skies. From the stellar winds where dust is born to the molecular clouds where it enables new stars and planets to form. From the chemistry on grain surfaces that builds complex molecules to the cosmic recycling that has been enriching the universe for billions of years. Space dust is one of those phenomena that seems insignificant at first glance. After all, it represents only about 1% of the mass of the galaxy, and individual grains are so small you'd need a microscope to see them. But, as we've discovered tonight, that 1% is doing an enormous amount of work. It cools molecular clouds, allowing them to collapse into stars. It provides the building blocks for planets. It facilitates the chemistry that creates complex molecules and potentially the precursors to life. It shapes the appearance of galaxies and influences their evolution. It carries the heavy elements created in stars back into space to enrich future generations. Without dust, the universe would be profoundly different. Stars might not form, or might form far less efficiently. Planets likely couldn't form at all, at least not rocky planets like Earth. The organic chemistry that leads to life might never get started without the surfaces of dust grains to catalyze reactions. The universe might be filled with nothing but primordial hydrogen and helium, unchanging and sterile. But we don't live in that universe. We live in a universe rich with dust. Dust that has been building up complexity for over 13 billion years. Dust that has enabled the cosmos to evolve from a nearly featureless soup of particles after the Big Bang into the rich, structured, living universe we see today. That dust is part of you. You are literally made of stardust, atoms that were once locked in grains floating through the galaxy, atoms that carry the history of stellar nucleosynthesis and cosmic evolution, atoms that will continue on long after your brief existence as a conscious being. In a way, studying dust is studying our origins. Every breath you take, every thought you think, depends on the chemical elements delivered to Earth by dust and the larger bodies built from dust billions of years ago. The water you drink contains oxygen atoms that once froze onto dust grains in a molecular cloud. The calcium in your bones, the silicon in the rocks beneath you, the carbon in every organic molecule in your body, all of it passed through the dust phase at some point in cosmic history. As you drift toward sleep tonight, I hope you carry with you a sense of wonder and connection. You are not separate from the cosmos. You are part of it. The same processes that created the dust drifting through the galaxy created you. You are the universe aware of itself, a temporary local concentration of stardust that has gained the ability to contemplate its own origins. If you've enjoyed this journey through the invisible architecture of the cosmos, if these gentle explorations have helped you unwind or given you a peaceful way to end your day, please consider liking this video and subscribing to the Sleepy Science Society. Your support helps us create more of these calm, curious wanderings through the universe's mysteries. And if there's a particular topic you'd like us to explore in a future video, leave a comment below. We read them all, and your suggestions guide where we'll drift next. The stars continue to shine, dust continues to swirl through space, and somewhere out there, in a cold molecular cloud, Dust grains are right now facilitating the chemistry that might one day lead to life on a world that doesn't yet exist. The universe is always creating, always recycling, always moving forward. And for now, you can rest knowing you're part of that vast, ancient dance. Sleep well, dream softly, and may your rest be as peaceful as dust settling gently through the silence of space. Good night.